So, ladies and gentlemen, we start our last unit, and we're going to try to get 5 lessons in this week. It puts us in a really good spot for when we come back from Christmas vacation. So keep up working, keep up with the homework. Try to work really hard on getting the vocabulary in. Today we start with a concept that's called the fundamental counting principle. And it sounds a little bit like probability or winning a lottery ticket. It's all about choices and opportunities. How many different choices or arrangements or opportunities do we have to solve a particular problem? Sometimes the problem can be drawn out, and our first introductory problem has been drawn out. Joe's shopping for a car, and he has 3 different models to choose from, and those 3 different models come in 5 different colors. How many choices of cars does Joe have? The tree diagram that's been shown is a nice, very visual way to show the number of opportunities he has. So it's good just to look at one in depth. Model 1 can come in blue, red, purple, white, or black. That's 5 different options. Model 2 can come in blue, red, purple, white, or black. That's another 5 options. And Model 3 can come in 5 different options: blue, red, purple, white, and black. And if we add the number of choices, we find out that he has 15 different car opportunities. And mathematically, we can represent that same calculation by taking the number of choices for the model. He has 3 choices for the model. He has 5 choices for the color. And that is equal to 15. That's our first representation of the fundamental counting principle, looking at the number of different opportunities or options there are for the choices we get to make. Let's look at our first example. So here I have a toy manufacturer, and we can create a tree diagram. I'm going to not do that in front of you today. If you'd like to verify the fundamental counting principle, you can draw the tree diagram associated with this problem. But how many choices is there for the first condition, part 1? Part 1 has 4 different options. Part 2, the middle part, has 3 different options. And part 3 has 2 different options. So I have a multiple number of ways to build this toy, and I can find the number of different colored toys that can be produced by multiplying these numbers together. 4 times 3 is 12, times 2 is 24. I've turned the page over, and I really want to emphasize the condition and. The condition and will always imply multiplication. We will have the condition of or when there is opportunities and the word or fits in, then the operation of adding will be our priority. We start with lots of multiplication, and I'll try to be specific as to when the or is coming. Class example 2. A Math 30 quiz consists of 8 multiple choice questions. Each question has 4 choices of A, B, C, or D. How many different sets of answers are possible? Here it's maybe helpful to think of the tree diagram option. Question number 1 could have 4 different answers, and question number 2 could have 4 different answers, and question number 3 could have 4 different answers. 5, 6, 7, 8, 1, 2, 3, 4, 5, 6. I wrote an 8. One, 2, 3, 4, 5, 6, 7, 8. For this multiple choice environment, I have 8 questions that have a possibility of having 4 unique answers. 4 to the power of 8 is a ridiculous number of options. Now we start with the idea of restrictions. Please note this bolded statement it's important that the restriction is dealt with first. Eric is dealing with odd numbers. They're odd 4-digit numbers, and the last number has to be an odd digit. And odd digits are 1, 3, 5, 7, 9. I have 5 choices for that last position. My first position cannot be a 0. But it can be any of the other digits that are possible. So any of the other digits include 1 up until 9 can be my first digits. So that's 9 different options for my first digit. And then in the last 2 positions, I can actually have any other number. I can have 0 to 9 and 0 to 9 in those middle positions. So that gives me 10 different options for my numbers or digits in that position. And now I get to multiply all those choices. 9 times 10 times 10 times 5. Now what happens if Eric has to deal with no repeating digits? Some of the first statements are still true. I still have 5 possibilities for my last one. So those are the numbers 1, 3, 5, 7, and 9. But now I have a problem with that first position. In that first position, I am no longer able to duplicate one of those. So instead of having 9 different choices for the first position, I actually have 8 different choices. And now because I can't have any repeated numbers, I end up reducing my choices here. So if we look at a particular example, just to think about that, there were 5 numbers here as a choice. If 1 was used at the end position, then I would have 2 through 9 for this position. And then if I just pick a number here, the number 2 was used for that first position, then I can use 0. I can't use 1, I can't use 2, but I can use 3 through 9. So that reduces my choices at that position to 8 numbers. And then again, if I take out one of those numbers, I'm going to take out the number 0. Then how many choices do I have left? Then I have 3 through 9 left, which is a choice of only 7 numbers. So now I get to multiply those choices together. 8 times 8 times 7 times 5 is how many 4-digit numbers there would be with no repeating digits. All right. Car number plates or license plates in Africa have a really weird system. They consist of any other letter than I or O. So any other letter than I or O. So that leaves me with 24 choices for my first position, followed by 3 digits. So 3 digits. And the first of which cannot be a 0. So those are the numbers 1 through 9. 1 through 9 and 1 through 9, which is a choice of, which is, I can have zeros here. I just can't have zeros on the first one. So 0 through 9 is a choice of 10. 0 through 9 is a choice of 10. But in that first position, I only have a choice of 9 digits. So I have digits, and then followed by any 2 letters which cannot be repeated. So now 2 letters which can't be repeated. Well, I used the letter at the beginning, and if that can't be repeated, let's check out the rule statement again. My 2 letters and their repetition is just related at the end here. So I have a choice of 26 letters for this position and 25 letters for the subsequent position. And I'm going to find the number of license plates possible in Africa by multiplying those numbers together. So multiplying 24 by 9 by 10 by 10 by 26 by 25 gives me 40,000 different license plate combinations. So another problem-solving style involves routes or pathways to get to places. How many routes are there from Pittsland to St. Luke's passing through Queensville? Take a look at the map. So if I look at my choice discussion, from Pitland to Queensville, there are 2 different roads I can take. And then from Queensland to St. Luke's, there's 3 different choices that I can take. So multiplying my choices gives me 6. Now if I go the other way, which is Pitland to St. Luke's through Rutherford, I've got 3 choices for Pittsland to Rutherford, and then only 1 choice to get to St. Luke's. So there's 3 choices there. How many routes are there to go from Pitland to St. Luke's? This is really my first OR situation. I can either go Pitland through Queensville or Pitland through Rutherford. So it's an OR statement. I can either do the upper path or the lower path. So guess what I get to do with my numbers? You're right, I get to add them. Let's take a look at a telephone number one with all kinds of funky restrictions. All right. 2 different scenarios. 3, 4, 5 must be there. And then I've got 10 times 10 times 10. There's only 1 choice for all of these numbers. They must be there. So it's 1 times 1 times 1 times 10 times 10 times 10. And then to that, I have to add 1 times 5 times 10 times 10 times 10. Remember, this is an OR scenario. So I've got 1,000 plus 5,000, which gives me the possibility of 6,000 different numbers for rural customers.